Hello, everyone. I hope you are all well. In this lecture, what we will do is we will discuss some of the topics that remain in the concepts of the fundamentals of mobile communication. And in particular, we will talk about frequency band allocation. We will focus on this and on resource block at the start of the lecture. And in these two topics, we will actually look at it from LTE point of view, and then once that's covered, then we'll go back into the fundamentals of communications, and we'll talk about frequency reuse, clusters, sectors, and interference in mobile communication. In particular, we will look at co-channel interference, and we will quantify the signal quality, or the SIR, in the downlink. So we'll show you how to do that as well. So on to the lecture. So far, we have seen some of the basics of mobile communication. We also studied mobile communication in Project 3. You've done that with Zohra in the first part and the second part. And in this lecture, and particularly in this slide, I wanted to discuss more frequency bands, the frequency bands related to mobile communication, in order to get a better understanding of what it means and what are typical values that you would see when you talk of current mobile systems. So mobile systems that we have today in 2020. Of course, as you know, we are entering gradually into 5G, but the network for us here in Canada is not here yet. So we will talk about LTE advanced technologies in the frequencies and the values that we have today. So I won't discuss specifically 5G, I'll discuss specifically 4G, but just be mindful that this will change in coming years. So when you study mobile communication, in this case LTE technology, you might see tables like this. Now this is a table that I put together last night, and it took me some time to get the data from different places and to make sure that the values are consistent and accurate. So I tried as best as I can to put it there. So you might see something like this. And I know that Zohra, she put a table similar to this, perhaps less information in it, but still quite similar to it on your project number 3. And you've done your project, but now we will go into further explanation. So if you see here, my objective will be to really go one column after the other so that you get a better understanding of what these terminologies mean and how they all come together. Because when we talk about frequencies, sometimes it could get overwhelming. You might hear terminologies like operating frequency or carrier frequency, or uplink frequency, downlink frequency, and lower, center, higher frequencies, and channel bandwidth, downlink, uplink bandwidth, duplex spacing, band gap, and all that. So you might hear these different things, but what does it mean physically? It could be a bit overwhelming. So we'll try to show you this in a visual way, and hopefully that will make it a bit clearer. I do recognize that it's not easy to get it right away, but I'll try my best to explain it as best as I can. Now, so these bands that I will discuss are essentially these bands. It doesn't mean we don't have others. So we have certainly other bands here in Canada and in other places, but these are the most famous ones that are used for LTE here in this country, in Canada. And I will specifically show you examples used by Bell, Telus, and Rogers. Right? Why, you might ask, why am I only discussing Bell, Telus, and Rogers? Well, because if you look at the numbers of subscribers that they have, it is the largest, right, in Canada. So Bell, they have somewhere around 10 million subscribers. Same thing with Rogers, and roughly the same thing with Telus. So that's the number of subscribers that they have. And in mobile communication, the number of clients or subscribers that you have gives you greater weight, right? You're more important by the number of subscribers that you have. That's just the way it is. So we could draw something parallel to standardization. We talked before about standardization, how mobile communication is standardized across the world. There is a body to do that, and we said that the 3GPP standardization body is the body that prints and publishes the standard for mobile connectivity. When you go to these meetings, or when these meetings are held, different mobile carriers attend. Other members of the mobile communication community show up as well. People that are involved in hardware fabrication for cellular communication, such as Ericsson, Nokia, Huawei, and others. Even cell phone manufacturers, sometimes they attend these events as well, like Samsung and others. So that's how these meetings occur, and through consensus and elections and so on, a standard of a technology is brought about. And in these events, the weight of how many subscribers you have gives you greater weight and more influence in 3GPP events, right? So if you look at Canada, we are the second largest country in the world. In mobile communications, we are quite minuscule. We're not that big. Our population is 35 million people. These three different companies, three Canadian companies, we only have 30 million subscribers. So compared to other mobile carriers around the world, we are extremely tiny. So for instance, you could compare it with China Mobile. China Mobile, they have 900 million subscribers. So compared to them, they are 90 times bigger than each of these different companies. So this is also something interesting to be minded of. But nonetheless, in a Canadian context, I will discuss only these three different companies. Other companies like Shaw Communication and Videotron in Quebec, they have some subscribers, but it's nowhere closer to these ones. Okay, so let's get going. Now, a good way to understand these different metrics and values is, like I said earlier, to look at it visually. So I give you this visual display here that I did earlier this morning, and I hope that that's going to help you understand these values. So number one, when we talk about LTE technology, there are different bands. And these bands, they have numbers. So they're numbered from band 1 all the way to, I think there are, perhaps 60 or 80 bands. I could be wrong on it, but there's a lot of bands. The ones that you saw in your project, maybe you saw a table with 30 bands. And if we go through these 30 bands, the most famous ones that we have that are utilized today by these three carriers in Canada are really band 4, 7, 13, and 17. Doesn't mean it's only these 4 bands. There might be others as well. And in fact, there are other bands that are used by Bell, Telus, and Rogers. But these are the most famous ones that are used today in our society. So probably your phone will operate in one of these bands. Okay. Now, these bands, they are defined by the 3GPP standardization body. And RL means release 8. So they publish different decisions that they make during these meetings, which they have annually, sometimes semi-annually. And this was published in Release 8. Band 17 was defined and published in Release 8.3. So this is also something to be mindful of. Sometimes these bands are referred by their other names, right? So if you want, the most basic way to refer to these bands is simply by their number. So band 4, band 7, band 13. But sometimes people use their kind of common name as well. So they have different names here. I put them on the table. You don't necessarily need to know this, as long as you could refer to it as LTE band 4, LTE band 7, band 13, band 17. That's more than enough, and that should be clear for people when you talk when you're trying to convey a message. You could just say the band number, that should be sufficient. What is more important after knowing the band number is to know at which frequency it operates. Remember, we saw in maybe lecture number 2 or lecture number 3, we went through the most famous technologies, the most famous wireless technologies, and we discussed their operating frequency. Right? So, for instance, we talked about Bluetooth, Zigbee, Wi-Fi, satellite communications. We talked about V2X. We talked about different technologies, and we went through their typical operating frequency. So, for instance, Wi-Fi is a very famous technology. We said that it operates at 2.4 gigahertz and at 5 gigahertz as well. So it has both capability, and we discussed on when it makes more sense to use 2.4 and when it makes more sense to use 5 in class. So for mobile communications, the frequencies that at least are important for us in Canada are the 700 megahertz. So, I mean, here I wrote it in terms of gig. So this reads as 0.7 gigahertz, but if you change it to engineering notation, it is 700 megahertz. 700 megahertz, that's a famous operating frequency for your mobile to work. 1.7 gigahertz, it's another famous operating frequency that we saw. 2.6 gigahertz is another known frequency that we generally use in this country. So these are the general frequencies. And we said with 5G communication, we will have new frequencies that will be introduced. And in particular, we said that in the sub 6 gigahertz, we will have a 3.5 gigahertz that will be introduced soon, and we should also have a 28 gigahertz that will be introduced soon. And in fact, these two numbers are not only for Canada, for us here, but they are also numbers that will be used probably in other places as well. Not probably, but it is the decision that's been made in different places around the world, in the US, in Europe, and in different places in Asia. So that's coming in later on. It was expected for 2020, but because of the various disruptions that we have right now in the world because of COVID, it's going to be pushed probably to 2021, at least here in Canada. So that's that. This is so when we talk of operating frequencies, that's kind of the shorthand explanation of at which frequency does your signal travel, right? Instead of saying all this mumbo jumbo here, you could just condense it and just talk about the operating frequency. But this is not very detailed, right? It just tells you it kind of gives you a big picture. You can think about it as a book, and in a book you have a title of a book, right? So that's kind of the title of the book. It doesn't explain to you the details in the book, it just gives you the title of the book. So when we talk of operating frequency, it's just kind of a big picture of what it is, but you have no idea of the details. And that's why you then open the book and see what's inside it, all the different details that you have in it. So that's that, okay? The other thing here, the column here that you have is called Duplex Mode. You perhaps can recall from lecture 2 or lecture 3. I honestly don't remember. You could go through Slate and look at the lecture number that we discussed that. We saw different type of duplexing modes, right? So we saw what is a simplex communication, what is a duplex communication, what is a half duplex communication, what is a full duplex communication, right? We went through that. And if you recall very quickly, a simplex communication, we talked about, we saw two different examples of that. For example, AM and FM, although it's analog, it's not digital communication, but it's still a simplex communication. You have a tower that broadcasts a radio signal. And you have a radio device that receives the signal. So you can only receive signals, you cannot transmit, and that's an example of a simplex communication. You have satellites in outer space, and these satellites, they are transmitting signals, and you have a phone. In your phone, you have an antenna, a GPS antenna that could detect signals from a satellite And you need at least 4 satellites to know where you are in 3D in space. And so at any time when you're outdoors, mostly you'll be able to you'll be able to see or detect signals from 4 satellites. And this is an example also of a simplex communication. You can only detect a signal. You cannot send a signal to a satellite. That's a simplex. And then we saw duplex communication. We said, for example, a two-way communication device or a walkie-talkie. That's an example of a duplex communication. You could receive and you can transmit. So it has a transceiver capability. But you cannot do it at the same time, right? You need to give it some gap. You have a certain time slot at which you can receive, and at a different time slot you can transmit. And we referred to this as half duplex, right? We saw that half duplex technologies, they are essentially based on TDD, time division duplex. We also saw a frequency division duplex, what we want to talk about here, where you can transmit and you can receive at the same time, but you transmit and receive using different frequencies, right? And when you do that, we saw some examples of that. Essentially, the most famous example for doing this is mobile communication. With a mobile communication, you can transmit a signal and you can receive a signal. You can talk and listen at the same time. Not necessarily recommended, but you could do that from a technology point of view. You could talk and listen at the same time from a technology point of view. And because you are transmitting at a certain frequency, and you are receiving at a certain frequency, and you are transmitting at a different frequency. So this is downlink, when you get a signal from the tower to you, and this is uplink, when you get you send a signal from your device to the tower. So in mobile communication, FDD is very important. That's the key duplexing mode that we use. So we will talk of that. And that's why you have here on the screen an x-axis with frequency on it. And we said all wireless communication technologies will operate in gigahertz. That's why you see gigahertz. Now, sure, you might say these two are not gigahertz. They are in megahertz. But nonetheless, the majority of signals in wireless communication, they are in gigahertz. Okay, so that's something that you should know. Now, the next column that we have is we have uplink. Uplink, we said, is when you have a signal that you go from your device, from your UE to the E node B, to the tower. That's uplink. And then next to it, you have downlink, where you have a signal coming in from the tower to your UE, to your device. Okay? And you will see that there are 3 different columns. There's a lower end to the uplink frequency, there's a higher end to the uplink frequency, and there's a center frequency. So there's that. And the same thing with the downlink. Now, why did I put the column for uplink here and the downlink after? It's because in reality, most of the time, uplink always happens at a lower range of frequencies as opposed to downlink. And that's why I wrote here usually. It's not always true, but usually that's the case. Downlink, when you get a signal from the tower, it operates at higher frequency, and uplink operates at lower frequency. Right? So if you look at band 7, these frequencies are larger than these frequencies. If you look at band 4, rather, this is what you observe. In band 7, the same thing. These frequencies are larger than these ones. Right? The downlink frequencies are larger than the uplink frequencies. In band 17, the same thing. These frequencies are larger than these frequencies. So the downlink is always operate at a higher frequency as opposed to the uplink. It operates at lower frequency. There's only one exception, and that's with band 13. There might be others, but in terms of these 4 bands, there's one important observation is with band 13. With band 13, it's done the other way around. So the downlink operates at lower frequency. It should be here, the downlink. And the uplink operates at higher frequency. So that's the only exception. But the rest, usually, as I said, this is how it should look like. Okay? What else is important here is the low, center, and high. Now, how do you get them? Well, this should be given to you, right? This is given to you. This is something that is published by the 3GPP standardization. So that kind of defines the frequency, and it's also regulated by the agency in every country. So for us, it should be approved by the government to operate at this frequency. So the lower end for LTE mobile communication for us, when you do an uplink, right? When you do an uplink, the lower end for the frequency, it's from 1.71 gigahertz in band 4 to 1.755 gigahertz. How do you find the center frequency? Or is it important to find the center frequency? Sometimes it is, and that's why we find it, but this is not necessary. This column is not necessary. You could forget about this column. I just did it because sometimes it's useful to know what is your center frequency. How do you find the center frequency? Well, that's easy. You take the higher point, you subtract it from the lower, and that gives you the bandwidth here, which is referred to as the uplink bandwidth. You divide it by 2, that gives you this region, and then you add it to the lower value, and then you'll be able to find the center. So again, you take this minus this, then you divide by 2, and then you add it to this one, and that gives you the center value for your frequency. So you could do that for all the different bands, and that's what I did here in this table. Now, the other thing that is useful to observe is the uplink bandwidth, so BW for bandwidth, and downlink, DL for downlink, UL for uplink, and BW for bandwidth. So the uplink bandwidth, the overall range here, and the overall range here, you could find it, you basically just take this minus this, and that finds you the bandwidth, right? So 1.755 minus 1.71 or 2.155 minus 2.11, they both give you the same thing. It's 45 megahertz. And you could do the same thing for the other bands as well to figure this out, okay? So you could find this region. That's the downlink and uplink bandwidth. The other thing that is important to know is that when you operate your phone, so anytime you use your phone, you will not be given the entire bandwidth here for downlink and uplink. This might be shared with other people that are using this frequency or this band, operating with one of your carriers. This might be used by others. So you will only get a slice of it. The slice that you use, this is referred to as a channel bandwidth. This is your channel bandwidth. And there are different providers. So for instance, if you look at band 4 and you have a Bell service, you either get a channel bandwidth of 10 megahertz or 20 megahertz. But if you're using band 4 and you're using Telus, you will get 20 megahertz, right? So it's just something to know. If you're using band 7, all the famous carriers that we have in Canada, they give you 20 megahertz. If you use band 13, they give you 5 megahertz. If you use band 17, 5 megahertz. So of course, you want higher bandwidth. The higher the bandwidth, the faster your connectivity. But also perhaps it goes up with price as well. So you have that this thing to observe. Okay. So sometimes you might be dropped to lesser bandwidth on band 13 and 17 because the upper ones are busy. They cannot provide you. They're busy, so you're dropped to a lower service. Or, for instance, you are paying less to the providers, and therefore your channel bandwidth is not the best, right? So you get a less performant connectivity with your tower, right? So, but in general, you want the higher frequency. That's better, always better for you. So that's the channel bandwidth. Okay. So channel bandwidth, just be mindful, it will not take the entire width of the frequencies that you have for downlink or for the uplink. It's only a slice of it. Only a slice of it. The other thing that is important to know here is the duplex spacing. This is very important. Duplex spacing, basically, because we said that in this region, you won't use all of it. You'll just be using this when you make a phone call or when you check your phone to check your email on your phone. You're only using a slice of it. The two slices, you want to have a gap between them, right? So imagine if your slice here was closer this would not be this is okay, you're still far away, but you want this gap to be farther away from each other. The larger this duplex spacing is, the better it is. The less the potential of crosstalk is better. There won't be collision between transmitting and receiving. Right? So you want this to be large. So if you look at this, the space between the channel when you transmit and the channel when you receive, the spacing between them can be measured, let's say, from this point to this point, or if you want, you could have measured it from here to here, it doesn't matter, or from its middle to its middle, it doesn't matter. You could just measure it and get a value. Of course, the larger, the better, but the others are fine as well. Okay, so you could get this, which is referred to as the duplex spacing. The other thing that might be interesting to observe when you have FDD, right? So this chart essentially, if I were to summarize it, I could just say this is an FDD chart, right? You have certain frequencies for downlink and certain frequencies for uplink. So the other thing that is necessary to look at when you have an FDD chart is the band gap. What is the gap between the downlink frequencies and the uplink frequencies? This thing here, and this is the band gap. You just take this one minus this, and that gives you the value, which is here. So in this case, if you look at this, you could take this, that's the low for the downlink. You subtract it from the high for the uplink, and that should give you this value here. Okay, so that covers all that we need to have for this table. So I hope that kind of gives you an explanation of how to read this table. The other thing that I wanted to mention with frequency bands is the following: is that when you send a signal, remember that we said, and we showed you this when we talked about the OSI model. We said about the OSI model, and then we showed you the different layers of communication. We said when you talk about telecommunications, there are seven logical layers, 7 layers. We refer to them as the OSI layer. And the most basic layer, the lower layer, is referred to as the phi layer, or the physical layer. And the one layer, it's also referred to as layer number 1. The layer above it is referred to as the MAC layer, right? That's layer number 2. And both of them together, they're referred to as the link layer, which is the lower layers. As electrical engineers, we are always in the lower layers, right? Layer 1 and layer 2. That's generally where we live. That's generally the work that we do. Sometimes we might also move to the network layer, but in general, we remain at the phi and at the MAC layer. And then as soon as you go to upper layers, then these layers become more relevant for people in computer science, computer engineering, and for people in applied computing and in computing and in these different fields, right? The people that design apps and so on. So, but for us, for electrical engineers, people involved in the circuitry and in building a circuit for communication and in looking at it from a system point of view, the phi layer is very important and the MAC layer is very important. And at the phi layer, we said that the most basic measure for data is bits, right? We said bits is the most basic way for us to look at a data. At the MAC layer, we will talk about essentially frames, right? So we'll talk about frames. And then you'll have a bunch of frames that is transmitted. So if you look at this, this is a chart of a frame. It gives you a chart of a frame, and you have these small squares. And in reality, these squares, they are referred to as resource blocks, right? Resource blocks. So every time you send a message, any data that you're trying to send or receive, you are basically sending a bunch of frames in your signal. Or if you want, essentially, let's put it this way. So maybe I should explain it in a better. So if you put a collection of bits together, these collection of bits together, they form a frame. Or in reality, they form a frame. And a frame is made of subframes and of slots. But let's just say it's a frame. And the frame, if you put various frames together, you put together a packet. That's what it's referred to. And if you put various packets together, you get a segment. And then segments, if you put a bunch of segments together, you get a data. That's how data is looked at. In each of these words, they are associated with a certain layer of the OSI model. So for physical layer, layer number 1, we usually talk of bits. Essentially, that's what we talk about, bits. For layer 2, MAC layer, we talk of frames. And then in the network layer, we talk of packets. Okay, so that's something that you should know as well. If you look at one of these blocks, this is kind of the most basic elemental component of a frame, and it's referred to as a resource block. Each of these resource blocks, they have a size of 0.5 millisecond, and they have a duration of 180 kilohertz. So when we talk of bandwidths in mobile communication with LTE, we said our typical bandwidths are 5, 10, and 20. 5, 10, and 20 megahertz here in Canada. And so if you look at it and somebody asks you, well, how many resource blocks are you using? So this is how it is, right? So you could figure this out, right? So if you take 25 times 180, this will be a bit less than 5. And if you take 50 times 180, it will be a bit less than 10. And if you take 100 times 180, it will be a bit less than 20. But these are the number of resource blocks that are needed. And when you design a system, a communication system, knowing the amount of resource blocks is very important. This will be kind of essential for you as you design your system, because you have, again, you have different users that are competing for these resources, and you have to use your resources wisely. As we said, frequency is not an infinite resource. It's a limited resource, and you have to use it wisely between yourself and all the other people that are trying to access your the technology. So in here, you want many people to use the mobile communication technology, and therefore you want to use your resources in a smart way. And that's why knowing the most basic fundamental, knowing how many resource blocks, how many of these squares you'll need for your communication will be useful and important. This is a big topic. There's a lot to be discussed here, but it will be way too advanced for this course. So we're not going to discuss that. I just wanted to introduce you to the concept of resource blocks. Okay, I think that covers it for this. At this point, I think we are ready, and we have a lot in our mind. We've learned a lot. We have some insight into what frequency bands mean in mobile communication, and now I want to talk about how we can use that as we assess and we design a mobile network. So we'll talk about that on the next slide, and we'll focus on frequency reuse. At this point, we became familiar with the concept of bandwidth, in the channel, really the channel bandwidth of a mobile technology. In the previous slide, we saw it specifically for an LTE. And right now, I will just explain it generically to you without necessarily connecting it to a specific technology, so that you understand the idea behind frequency reuse. So in general, just in general, the whole point of frequency reuse is as follows. We have many users, and we want these users to have access to some mobile connectivity. And this is not always easy because the frequency is limited. So let's begin. So as you see here, what I wrote is the following. Although radio frequency is a limited and finite resource, it is desired to provide mobile connectivity to as many users as possible. Remember, we saw in the previous slide, we said every user that will use that wants to communicate using a mobile device will need a channel bandwidth. However, the channel bandwidth, you take it from the spectrum, right? The RF, the radio frequency spectrum. And as you saw in lecture 1, the radio frequency spectrum is limited. You have a certain range, and that's it. If you use it, there's nothing we could do. It's done. It's limited, and it's finite, and if it's used, there's nothing you could do. You cannot accommodate other people. So how do you ensure that many people hundreds and thousands of people can use the service, a mobile service, with a very limited frequency. This is where different techniques are available. These techniques that are available that allow multiple users to use the technology, to use the cell phone technology at the same time, is referred to as multiple access scheme. Multiple access scheme. And there are different methods in multiple access scheme. Different people have, and engineers and researchers and companies have experimented and tested with different technologies. Some of them became standardized. It saw the light, and it was used by in real life, and some of them did not. So I'll just mention very quickly that, for instance, Fdma, frequency division multiple access, was a technology that was used. And essentially what it means is you have a certain frequency range, and you slice that frequency into small chunks of bandwidth. Every bandwidth will be dedicated and assigned to a specific user. Okay, that was Fdma. This was used in 1G technology and in 2G technology. There was also another approach of multiple access scheme known as Tdma, time division multiple access. In time division multiple access, you had the frequency, the entire frequency. The only difference is that the time when you can send your signal was chopped, right? So in certain time slots, you can send your signal. So it's kind of similar to what we saw earlier with TDD. That was used also in 2G in addition to Fdma. Eventually, it came. There was a new technology that was introduced for 3G. It's known as Cdma, and in Cdma, you had all the frequency that was available. You could have used all the frequency and the time, so it didn't depend on frequency and time. It varied with code. This is a bit hard to explain, so perhaps I'm going to use an analogy here. So essentially, you could think of it as though you're in a room and there are different people in there. Let's say there's 5 people in the room, and 2 of them will speak English. The other 2 will speak, I don't know, French, and then the other people in the room will speak German, right? So you have different people in the room; they speak differently, different languages. So they could all communicate, but you can only detect those that you understand the language of. And that's why it was secure, because you could use codes for that. And that's known as Cdma. There's more explanation to that. I just made it very simple in that explanation. Eventually, in 4G and in 5G, we are now using something called OFDMA, so orthogonal frequency division multiple access, and now in 5G, it still uses OFDMA. That's proposed with the addition of non-orthogonal multiple access scheme known as NOMA. So that's also used. But for now, in order to explain to you frequency reuse, I'm going to use the technologies that was very cutting edge during 2G. 1G and 2G during the GSM technology. By the way, it's still around. Some countries still use this technology. And therefore, I'm going to use that to explain you frequency reuse. But then we'll see. You'll see in advanced courses how that modified, and eventually what we're considering right now is OFDMA and NOMA. So let's move on. So this is the whole point. You have many users, but you have limited frequency. So how are you gonna divide your resources to them accordingly? And we'll see the different techniques that are done here. So by definition, cellular communications allow a set of frequency channels to be reutilized over different areas so as to enable connectivity to as many active users as possible. So you have a limited amount of channel bandwidth, but you have many users. So the way you do it is that you recycle these frequencies, you recycle these bandwidths. So in a certain area, you use a certain amount of bandwidth, and in some neighboring area, you could reuse these bandwidth. And the hope here is that this neighboring area is not very close to you, so that interference doesn't happen. That's the hope. right? So you want, otherwise there's nothing, we can't do anything, right? So you want to have many people to have connectivity, and that's the only choice that we have, is to reuse these frequency bands. Right? And this is known as a frequency reuse. So this technology, this is technically known as frequency reuse, or FR. We sometimes use the word FR. So if you were to boil down the concept of cellular communication, we could say that cellular communication is founded on the principle of frequency reuse. The whole point of having a network of cells in these kind of circular or hexagonal shape is because in each of these regions, you use a certain frequencies, and in neighboring adjacent cells, you will reuse the same frequencies, right? And that's the whole point of cellular communication, is to divide the network in these cells. It will be more clear as we move along. So, certain frequency reuse design guidelines must be applied so as to allow many users to connect while still ensuring co-channel interference is minimized. This is kind of the big thing that you should realize, is that we will reuse the frequencies, but we have to be careful when we reuse the frequencies that was already used by some other cell, some other neighboring cell. Because now that you have two different base stations using the same frequencies, you will end up having interference. So you have to coordinate, and then you have to do to manipulate this and the scheme in order to minimize what is known as CCI, or co-channel interference. You want to minimize this as much as possible, and there are certain guidelines around this. Most of it depend on geometry and also on the location of where the channel is, and we'll see some of it in this lecture. This is also a big topic. It also evolved from different generations, from 2G to 3G to 4 to 5G, but we'll try to keep it very fundamental here so you get the gist of it. Now, in frequency reuse, when you have a frequency reuse, you will essentially be required to form a cluster, certain clusters of cells. So I'll show you some examples of cell clusters. So this is one cell cluster. Essentially, you have one base station. So you have an E node B here. This is the coverage of it. And we said we're going to use hexagonal shapes because that makes analysis easy. And if you need to understand why hexagonal, I made a full lecture to give a sense of why we use hexagonal. So we use that. So that's considered one cluster. It's just one cluster. The size of the cluster is 1. And then in the cluster, there's just one cell. This is another cluster. The size of the cluster is 3. There's 3 cells, and all together, they form a cluster. That's why the surrounding of it is bolder. Right? So this is one cluster. And you have certain amount of frequency channels here, another set of frequency channels here, and then the rest here. And the frequency channels here, they are unique to this one. The frequency channels here are unique to here. It's not the same that you have in A. And the frequency channels here are unique to this. We refer to that with these letters, A. So A, you could think of it as a set. And within the set, you have a subset of channels. So let's say channel 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then this one will have, channel 21 all the way to channel 40. This one will have channel 41 until 60. Listen, I'm just using this as an example. It depends on how many channels you have, how your uplink and downlink bandwidth was divided into how many channels. So that depends. But that's kind of the idea of what a cluster is. So this is the size of the cluster. 3 is the size of your cluster. 1 is the size of the cluster. This is another cluster. You have a cluster here of 4 cells, and that's what you get. This is another size of a cluster. You have a cluster now of 7 cells. So if you count them, there's 7. 1, 2, 3, 4, 5, 6, 7. And in each of them, you have certain channels. Here you have some channels, here the rest, and so on. Here you have another cluster, a cluster of 9, and here you have a cluster of 12. Now you might ask, well, hold on, why is there no cluster of 2 cells? Or why is there no cluster of 5 cells or 6 cells or 8 cells or 10 or 11. There's certain rules around forming a cluster, and we'll explain it later on to you on the next slide, which cluster sizes are valid and which cluster sizes are not valid, right? So we'll explain that. Also, why is the shape like this? Can you have a shape of your choice? The answer is no. The shape is is like this because of certain guidelines. We have to follow the certain guidelines that tells us why the shape is in a certain way as opposed to another way. Now, these are all methods that have been proved to be the most effective way for forming a cellular cluster, and that's why we follow these guidelines. So I'm going to explain that on the next slide. And by the way, before I move on, I should also mention that, for instance, this one here, cluster of size 4, this is one possible shape that is valid. You could also have another possible shape that is valid. So sometimes you'll be able to form, for a certain cluster size, you have some shapes that work and some that are not valid. So this is, for 4, this is valid, but there's also another one that I'll show you later on. It's also valid. So this is something that you could be mindful of. Now the question is, how do we get this? How do we find the valid cluster size? We'll talk of that on the next slide. At this point, we are ready to move along and to see what are the guidelines in determining the proper cluster size. So as we said, not any cluster of choice is valid. There are certain guidelines here, and we will show that at this point. And then once we determine the cluster size, then the next step is to allocate channels to each of these, to each cell within the cluster, right? So that's what you want to do. And this is referred to as Fdma. And I'll explain that as we move along through this slide. So the way that clusters are assigned, they follow this equation. So this is an equation that was derived in one of the peer-reviewed papers, and it became the standard at determining the number of clusters when we work with hexagonal cells. So the way it works is as such: NFR, FR for frequency reuse, and N is the number of cells that you have within a cluster, is equal to I squared. I is just some number that is an integer, and J squared, so J is another number that is also an integer. This number could equal I, or it could be less than I, plus the multiple of these two integers. Okay, so this is just a mathematical way of saying that both I and J are integers, and they are element of the set of natural numbers. That's what it means. And then, like we said, J is could equal to I, or it could be less. So if we you could try different integers to see what you get, but I did a table here for you with different values of I and J. So for I, we begin from 1, and we could go all the way to whichever number you prefer. And for J, we begin one less, a less than 1, so that's why we begin from 0. And we could also proceed as much as we want. But I wanted to stop to numbers, cluster sizes that are below 20. But you could have certainly continued, and that's why I put dot, so for you to continue if you're interested. And this is what we have. So let's say you put I equals to 1, and you put J equals to 0 in the equation. So I is 1, so 1 squared, that's 1, plus 0 squared, that's still 1, plus 0, and therefore you get 1. Let's say we do 2, 1, so you do 2 squared, that's 4, 1 squared, that's 1, so that becomes 5, and then 2 times 1, that's 2 plus 5, so that becomes 7, and that's how you get 7. But you could get 7 either with I equals to 2 and J equals to 1, or you could get 7 with I equals to 1 and J equals to 2. So it doesn't matter. Both of them will get you 7. And then you could try this with other combinations. So as you see, sometimes you could get a certain value with two different ways, and sometimes you could get a value with only one way, right? So like for instance here, you get a 4 with 2 0. Right? That's a possibility here only. Okay, and the same thing with 9. So you get a 9 with 3 0, whereas 13 you could get it with 3 1. Or with 1 3, right? You just flip the integer values. So if you do a list of this, we can actually enumerate the valid cluster sizes, and we notice, and if I enumerate them from the smallest to the biggest, valid cluster sizes are 1, 3, 4, 7, 9, 12, 13, 16, 19, and so on and so forth. If you continue the table, you'll figure others. You don't need to do all that. In fact, in real life, you will never have cluster sizes beyond 7. So real life will be here, anywhere between 1 to 7. And in fact, today with 4G and with 5G, we're mostly at 1. And I'll explain what that means later on, but we are here. But historically speaking, as we moved from 1G to 2G to 3G to 4G, it varied between these ones. The others are just mathematically possible, but they are not relevant for practical purposes. So at this point, I wanted to then, now that we've seen how the cluster size is obtained, I'll just show you how we could allocate channels to each of the cells within the cluster. So if we go back to what I showed you earlier in this lecture, right? We showed you earlier in this lecture, you have an FDD, a frequency division duplex. And in the FDD, we saw, so this is what we saw from there, that we have, in general, in the lower frequencies, we have the band for uplink, right? Uplink. So when you go from your UE to the E node B, and in the higher frequencies you have for the downlink, when you go from the E node B to the UE. Okay, and then you have some gap between them, and you want this gap. This is referred to as band gap. Okay, so if we have this and we decide to chop this bandwidth for both, for the uplink and downlink, for a certain bandwidth, right? So you want this bandwidth. Now, if you have a large bandwidth, that's great. You will have fast connectivity. If you have a small bandwidth, that's not so great, but you know, what can you do? If you have too many users, you will end up with smaller bandwidth. So you'll accommodate more users that way in an Fdma point of view. So this is really, just to clarify again, this is really an explanation that is practically relevant for 1G and 2G, not for 4 and 5G and 3G. I'll explain what happened after. So in this sense, in an Fdma point of view, what we do is we chop the band, the uplink band, into small slices. And every slice is a channel. So this is channel 1 and up to channel 9. It doesn't mean you only have 9 channels. This is just an example that I'm showing you here. Perhaps you have 20 channels. Perhaps you have less. Perhaps you have a bit more. But this is just an example. Here we're doing an example with 9 channels. So whatever the specific uplink bandwidth is, we just divided it into 9 slices. They are all slices are of equal sizes. And you could do the same thing with the uplink. We know that the uplink, you could do the same thing with the downlink, right? You have your downlink and you chop it into small bandwidths, right? So these are the different channel bandwidth for every user. So you're a user, every user will have one of these when they make a phone call, and or one of these, or a combination of both. You need both, right? When you receive and when you send. So you'll have one of these slices, and that's the meaning of it. So if now we want to get a better understanding of what this means when we chop the frequency, it is essentially it has a name. So this name is referred to as frequency division multiple access, or Fdma. Now Fdma is a type of multiple access scheme. In reality, there are different multiple access schemes. There's this one, which is known as Fdma. There are others as well. There's Tdma, Cdma, OFDMA, and there's a new one right now for 5G that is referred to as NOMA. Now, FDMA, it means that the frequency, the slices for every user is chopped in frequency. So it's as though you have a cake and your cake is sliced up, and every user will get a certain amount of the cake. Now, if you have less users, your cake will be bigger, so you'll get more bandwidth. But if you have more users, your cake will be smaller and you'll have less bandwidth. And less bandwidth means, not the fastest connectivity, and also the performance also could deteriorate with that. But not the fastest connectivity. You have a smaller slice here. So this is just an analogy. So in this analogy, the cake represents your frequency, and every slice represents a user. And that's the same thing here. So every slice is a user. Okay. Now, if you do use Tdma, time division multiple access, then in that case, what we're slicing is we're slicing the slices, but we're not doing it with respect to frequency. We are slicing it with respect to time. So within a specific time frame, you'll be able to transmit for one user. Within the next time frame, the other user will be able to transmit, and so on and so forth. And Cdma is a code division multiple access, and that I talked about it earlier on the previous slide. OFDMA is a combination of both. So in here, in FDMA, what you're doing is you're slicing the frequency. In Tdma, you're slicing the time. In Cdma, you're actually slicing the power, right? So you get different codes, and then every code will have a certain power level. In OFDMA, you are actually slicing both time and frequency. And in this one, NOMA, you're slicing with respect to time, frequency, and power. So this is very comprehensive, and it's also a new multiple access scheme. And it's a very hot topic right now. Okay, so now you might ask which one is used where. So just for perspective, FDMA, it was used in 1G and in 2G. Tdma, it was mostly used in 2G, so GSM, so both of them are used in GSM. Cdma, mostly in 3G. OFDMA in 4G. And right now in 5G, it's a combination of both OFDMA and NOMA. Okay, and that's what's happening, and in fact, it's going to move more toward NOMA because this is a smarter multiple access scheme. So this is just for perspective. It's a big topic to discuss all this, and we don't have enough time, so we're not going to discuss in more detail. I just wanted to highlight it for you. For us, in order to explain the concept, we will focus on FDMA. And as long as you understand FDMA, that this is a good initial step in learning the others, right? It's a good step in learning the others. So now that we have this, let's consider, let's say, a cluster. And in this case, let's consider a cluster of size 3, right? A cluster of size 3, it seems like a reasonable number. In fact, since we're here, maybe I should mention that clusters of size 3 and of size 7, they are mostly valid for 1G, 2G, and a cluster of size 3 is also valid for 3G. Clusters of size 1 is mostly valid for 4G and for 5G. And I'll explain why we did that later on, and it's really because of the access scheme that is used, right? So it goes in combination. But now let's focus on cluster size 3. We have this, and as you notice, for each cell, so we have 3 cells within the cluster, we give them a letter identifier. So this cell is identified with letter A, and this one is identified with letter B, and this is with letter C. And these are the frequency channels that we have. So what do we do? In this case, what we do is we actually divide the channel. We say a bunch of these channels will be allocated to this cell, to this base station. The base station here will have a certain amount of channels. The other one will have the rest, and then the third one will have the remaining. And we do the same thing with here. So if we write it up, this is something that you could, for instance, have. So we could say that channel 1, 2, 3 for the uplink will be related to this cell, and channels 10, 11, and 12 for the downlink is related to this cell. For the next cell, cell B, you will have channels 4, 5, 6 related to it for uplink, and you will have channels 13, 14, 15 for the downlink. And for the cell C, you will have the remaining channels, channels 7, 8, 9 for the uplink, and channels 16, 17, 18 for the downlink. And this is what you see here, right? So the larger the cluster size, the less channels you will have, right? You will have less channels that you could work with, right? Let's assume we keep the size of the channel the same. We don't shrink the size here, the size of the bandwidth of each channel. We keep it the same, but we increase it to 4. Then what it means is so what you have is you have 9 channels, and you divide it to 4 cells. Let's say you have 4 cells. Then what's going to end up happening is that you'll have 2 in each. One of them will have 3. So you'll have one cell. Cell A could, for instance, have 2. Cell B could have 2. Cell C could have 2. And cell D, if we had a cluster of 4, will have 3. Okay. So that's one way to do it. So the more you increase the cluster size, the less simultaneous users you can accommodate, and therefore increasing the cluster size is not desired. But it is still used in order to take advantage of, in order to somehow accommodate the frequencies that we have to the number of users over a larger space, a larger surface area, right? A larger surface area. Okay, I hope this is understandable. You might need to kind of go through it multiple times and then to reflect on it to understand better. But I tried to make it understandable with pictures in this explanation. Okay, let's move on to the next slide. So far we've seen how the size of the cluster is identified and determined. We also saw how channels are assigned to different cells within the cluster. At this point, we're curious on the shape of the cluster. Is there a specific shape for clusters? Can you just pick any cells and that will form the shape of your cluster? Well, the short answer is no, you cannot do that, right? So once you determine the number for your cluster, the shape should follow a certain guidelines as well. There is an algorithm that one has to follow. In this algorithm, if it is followed as described here on this slide, it will essentially ensure that the co-channel cells will be at equal distances. Co-channel cells, basically all the neighboring cells that will operate with the same channels, that will have the same channels, will be at a similar distance. It will make more sense as I go along, but first I want to explain the algorithm. So I'll read you what I wrote here. Now, in order to have co-channel cells at equal distances, and this is important, that's why we use this algorithm, then neighboring clusters of a reference cell should be obtained using this algorithm. Number 1, select a valid cluster size, NFR. So we determined how to find that. We said that the typical cluster sizes that we have are 1, that's just one cell, that's your cluster with one cell. 3, that's a cluster with 3 cells. 4, that's a cluster with 4 cells. Or 7, that's another cluster with 7 cells. 9, and so on. In real life, we said that 1, 3, 4, and 7 make sense. Well, for 7 cells are typical with 1G systems that we had in the past. With 4 cells in a cluster, that's kind of typical for 2G cells. With 3 cells, that's kind of typical for 3G cells. With 1 cell, it is more relevant for 4G and also for 5G. There are some techniques right now. You might find some scientific peer-reviewed paper that would suggest different methods with beamforming and others where you could in fact increase the the frequency reuse from the typical 1 to greater numbers. So there are some techniques that are proposed in different places, but in general, 1 is traditional. That's what we have right now with LTE. So okay, so you select a valid cluster size, and we know the feasible set. So the feasible set is 1, 3, 4, 7, 9, 12, and so on. So you select one of them. Then you identify its associated IJ indices. We find that. So if you don't want to figure the IJ indice on yourself, you could just look at the table that I placed on previous slides. Right? There was a table with the IJ. So you look for the number, and then you find your IJ indices. So basically you do kind of reverse engineering. Then for a particular cell within the cluster, move I cells from one of the 6 sides. So you go to one of the sides, it's a hexagon, so you have 6 sides. You move I cells from that center point, from the place where the E node B is located, the place where the antenna is located. You move I cells. Right, so I cells, let's say I is 2, then you move 2 cells. Let's say I is 1, you move 1 cell, okay? After that, what you do is you turn counterclockwise by 60 degrees, and you move forward by J cells, okay? And then what you do is you repeat for all the other sides of the reference cell by going back to 3. You go back to 3, and then you do it for all the other sides of your hexagon. You have 6 sides. You did it for one side. Now you do it for the second one, the third, the fourth, the fifth, and the 6th side. And that kind of covers, it will let you identify all of your neighboring cells. All of your neighboring cells. These guidelines are very important so that network designers, those that design the network, the people that will deploy the mobile carriers, that will deploy the base stations around the city, will kind of follow that in order to have a more deterministic kind of approach to the deployment of a network. Today, this is hardly used because we have so many cells. So there are newer techniques, and in fact, the techniques became more advanced, but also more complex. And this is more relevant for 2G networks. It was a bit more straightforward and less complex. But I still want to focus on this because it is a first step in learning mobile communication. And then once you learn this, you'll be able to learn the more advanced schemes and approach for designing a mobile network over a large surface area. Okay, so let's show you some examples. So these are examples of clusters of 4 cells. So if you look at it, this is a cluster, right? And you have A, B, C, D, which means you have 4 cells. So it means your NFR is equal to 4. This is the same thing. There's also 4 cells, and it means your cluster is 4. So they're both clusters of the same size. These are also, this is also an example of a cluster with 4 cells. This is also another example of a cluster with 4 cells. But if you try it, and you try it with the algorithm, these cells are not valid clusters, right? So they're not valid. Now, if we do some of the numbers here, so we selected NFR, so we did the first step. We know that we want a cluster of 4 cells, and we went to the table that you had in the previous slide, and we noticed that in order to get 4, your I should be 2 and your J should be 0. So let's do it. So let's say this is your the one that you have, A, and you want to find adjacent cells that will also should have A. So what you do is you move by 2 cells. Let's do this side. So that's 1, and then that's 2, and then you turn by 60 degrees. So it means you turn by this, but you move by 0. In other words, you stay here. And so you found it. This is your first co-channel cell. Okay, so this cell and this cell, they will both have the same frequency bands, the same channels, and therefore this cell will interfere with this one, and this one will interfere with this one. They will mutually interfere each other. And you could do the same thing with this side. You move by 2, 1, 2. You turn by 60 degrees, but you don't move it with anything because your J is 0. So this is your your second co-channel cell. And then you do this for the other sides, and then you find it here. And this allows you to find the radius for your nearest co-channel. So you have a radius for your nearest co-channel. If you have this kind of cluster and you do it, you get this radius as well. So you move by 2, 1, 2, and then you found it. You move by 2, 1, 2, you found it. You move by 2, 1, 2, you found it, and the same everywhere, and you get this. So notice the following. Although with cluster size although you have selected cluster size 4, you got 2 different formation for the cluster. So clusters are not necessarily unique. In this case, with 4, they're not unique. Both of them work. This works as a cluster shape, and this also works as a cluster shape. And what is interesting to observe is that the distance to the nearest co-channel is the same. So they're the same, irrespective of which cluster shape you choose. For the others, for cluster size 1, cluster size 3, cluster size 7, and cluster size 9 and 12, I just found one shape, and then you don't need to figure out the shape. I already gave it to you, right? I already gave it to you in previous slides. So now what we notice is this. This is not valid cluster shape. This is not a valid cluster shape. This is a valid cluster shape. This is a valid cluster shape as well. And for others, you don't need to necessarily break your head to figure it out. I already did it for you. So you could always go back to slide 3 for valid cluster shapes. You have it from 1 to 9. I believe I placed it there, or to 12, and then that's what you need. And essentially, we said just 1 to 7 that are the essentials. The others are there just kind of interesting to see it from a geometrical point of view, but they have no practical relevance. Relevance is mostly is not mostly. It is basically anywhere from 1 to 7, and 7 was basically used with 1G, no longer used anymore right now. Okay, let's move on to the next slide. So now we've seen through a very systematic algorithm how the co-channels, the first tier co-channels of a cell are identified. So we saw that in the previous algorithm, and that's great. At this point, we could use this knowledge in order to really identify how interference can be assessed. Because at the end of the day, we want to measure the quality of the signal at a mobile. And this will require that we understand interference. We could look at interference from other different cells that have the same frequencies, that operate with the same channels. However, when we look at the interference, it is not a bad idea to always begin with the first tier. You can certainly go with second tier and third tier, but that becomes a bit too cumbersome. And also, not only is it too cumbersome, it might be you might be doing too much work with not so much of benefit, right? So the impact could be negligible. Although one has to also be reminded that interference is always measured at the aggregate. So I don't want to totally discard second tier and third tier interferers, but let's just focus on first tier for the moment. It will make the analysis much easier. And also, it is somewhat plausible to believe that second tier and third tier they will contribute to the interference, but it will be to some extent negligible. Okay, so let's look at this. So we have our cell. In this case, we considered a frequency reuse of 1. In other words, we have a cluster with only one cell. So all the channels that you have allocated, they're here. And all your neighboring cells, they will use the same frequencies. So if you have, I don't know, 9 channels here for uplink and downlink, the same channels will be here, right? The same will be used next door at neighboring cells. So the rules tells us to always go back to this. And if you have a frequency reuse of 1, you have a cluster of size 1. You come look at it here. This is your 1. It means your I is 1 and your J is 0. So you move by one cell, and this is it. You move by one cell and you found it, and that's kind of obvious. So you find your co-channel cells as such. Now, what if we have a cluster with 3 cells, and it's identified as ABC, and we want to find all the co-channel cells for cell A. What we do is we notice that we are using a cluster of size 3. We come look at the table, we identify 3. 3 is here. 3 is obtained when I is 1 and j is 1, and therefore we could go through all the different sides. We apply the algorithm, we move by 1, we turn by 60 degrees to the counterclockwise, and we move by 1, and that's A. We go to this side, we move by 1, we turn by 60 degrees counterclockwise, and we find the next cell. This is the other A. We move by 1, we turn by counterclockwise by 60 degrees, and we move by another 1, and we find this, and likewise we do the other. So I did put the trace for you in order to really know how the algorithm works, right? So the trace here should help you see how we apply the algorithm to find the neighboring co-channel cells. Okay, now what if we have a cluster a cluster that is formed with 4 cells, and let's say we use this one. We saw that there are two different ways of getting a cluster, where this is highlighted and this is not. That's also possible, but in here I wanted to use this one here. It has an interesting symmetry to it, so I'd like to use it. So we have 4, and we look at our table. How did we get 4? Well, 4 is here. 4 is obtained when I is 2 and j is 0. So let's do that. I is 2, we move by 2, 1, 2, it's here, and we don't move anything on the j, so we stay here. 1, 2 here, 1, 2 here, and so on and so forth. So here, the trace to obtain your co-channel, just a straight line, because your j is 0, right? Your j is 0. Okay, so that's that. Now, what if we have a cluster of size 7? So what we do is we want to find all the other cells of size 7. We come here, we find where 7 is. So 7 is here and 7 is here. So there are 2 ways to get 7. Either we use 1, I equals 1 and j equals to 2, or we use I equals to 2 and j equals to 1. So both would work. In fact, by the way, I just realized that in the previous slide, I told you that j should always be less or equal to I. Now that I'm looking at the table, the way I did the table, this condition is not necessarily necessary. I and j are both integers. It doesn't have to be less or the other. So I use both of them. So this condition that I explained earlier is not true. Forget it. You could cross it off. So you have 2 options to get 7. Either you use 1 and 2, or you use 2 and 1. In here, what I used is I used 1 and 2. So I move by I by 1. I turn counterclockwise and I move by 2. And I found this one. For this side, I move by 1. I turn counterclockwise and I move by 2. I find this one. For this next one, I move by 1. I turn counterclockwise and I move by 2. I find this one. And the same. So you see the trace of how we applied the algorithm to find the co-channel interference. That's about it. Now, at this point, what I wanted to show you is this. What we are curious to know is, what is this distance? You are interested to know the co-channel radius, the radius between this cell and your neighboring cells that interfere. So what is this radius here? What is this radius here? What is this radius here? And what is this radius here? So there is a way to do that, and the way to do that will require some geometry. So I'll do it with you. Now, there's some math, but we'll go through it together. It should be very basic math. So if we look at the geometry of a hexagon by definition will have sides, and all the sides will have the same value, right? So they all have the same length. So this is, let's call it length L. This is length L, length L, length L. All of it has size length L, and this is the middle. and the other one as well. So let's stick two together, two honeycomb hexagons next to each other, and we are interested to find the distance between one point and the other when they are in this shape. So one thing you should realize is that now that you know that all the sides are of length L, also this radius, this value here, is also of length L, and this value here is also of length L. You could show this through some geometry that this is L and this is also L. And the point that it intersects is halfway L. If this is also L, so we are looking at half L. So this is L over 2. This is L. And now you're curious to find this one here. So you could do some Pythagoras. You could apply Pythagoras rule to determine the value here, this value here. And once you apply Pythagoras to find this value, you'll find that this value is in fact equal to square root of 3 divided by 2 times L. Now you have both sides, so here, and you'll end up finding that the dBs, so the distance between base stations, two base stations, or two E node Bs or two G node Bs, is actually square root of 3 times L. And that's the way that you find this value. So you could find it yourself, you could find it here, or if you're interested, I'll put some of my own work, some references there that shows you how to get this. Okay, so now that we know this, what we could do is the following. We could actually draw some generic cell. This is the reference cell. Let's say this is where your A is, and you want to find all the co-channels, the nearest co-channel cells. And what you do is, like we did in all these examples, we move by I points times D, dBs, this value here. So if you notice here, we move just by 1 dBs. Here we move by 1 dBs. Here we move by 2 dBs, right? So it's always the same thing. We move by a certain value of I times dBs, and then we turn counterclockwise by 60 degrees, and we move J times dBs. So here we move by 2 dBs, so because your J is equal to 2. Here we move by 1 dBs, and here we don't have any dBs, it's 0. But you could just put it at J dBs here. And the distance that you are curious to find is essentially the distance between this reference and all the neighboring cells. So you look at this, you have this value, it's here. You have this value, it's here. dBs, you know it, you found it earlier, it's square root of 3L. So you have that. And you want to find DFR, the frequency reuse distance, right? This is what you want to find. So if you look at this, this pretty much looks like is a triangle, and you could simply use the laws of cosines to find this. And so through the law of cosines, you could you have this, you want to find this, and you need to know this angle. If this is 60 degrees, then this angle will be 180 minus 60, and therefore this is 120. And therefore that you have everything that you need to do. You could just do this equation here, which is this distance squared equals to this squared plus this squared minus 2 times this cosine of this angle, 120 degrees. If you write 120 degrees in radiant, it's just 2 pi over 3. You do some math, you simplify, and then interestingly enough, you find that this equals to I squared plus J squared plus IJ times dBs. dBs, you know it, is this, but this is squared. So for now, let's just write it like this. And this thing here, I don't know if you recall, but this is basically your value for the cluster size, your NFR. So this turns out to be very nice, right? So this is an equation that we get. We put this in it, we take the square root, and eventually we get the co-channel radius to be equal to this. And this will be very useful when we estimate the SINR of a mobile device, right? This will be very, very useful to do that. So this is a very interesting result that we will show as we move along. So this is kind of how we got this. Okay, so let's move on to the next slide. So far, we saw the impact of interference when we have omnidirectional antennas. Right, our antennas of the base station antennas, the E node B antennas, the G node B antennas are omnidirectional. They propagate in all directions. We saw that, and we saw the impact of interference, and we realized that in fact, irrespective of the cluster size, we will have 6 interferers around them. And the reason for that is because we are working with a hexagonal cell. A hexagon has 6 sides, and therefore we'll have 6 interferers around it. And that's kind of more or less realistic to what happens in real life. Now, certainly we saw different models for coming up with the network, and we saw how for an eye diagram, sometimes you will have more neighbors, sometimes you'll have less neighbors than 6, more neighbors than 6. But in general, if we use a hexagonal model, you'll have 6 neighboring cells, and therefore, when the antenna is omnidirectional, you'll see 6 different first-tier interferers. At this point, we're asking ourselves, well, what if we have antennas that are sectored? So they are directional antennas. This is a picture of a base station, of an E node B, where the antennas that you have are sectored. So as you can see, you have 3 different antennas. They are totally independent, and they have a certain coverage region. So this covers a 120-degree region of where the antenna is propagating. It doesn't propagate in all direction. And this as well, the same thing, propagates within a region of 120 degrees. And then the same thing with the other one. If you add 120 times 3, that creates your 360. So you could have such a setup, and I'm sure many of you have seen this. They exist everywhere in the city. They exist today. If you've seen it on the street, you would notice these kind of antennas. So if we could show again the network plan of the cellular, and this time show it when the cells are split into 3. So I'll show you what I mean. So we have our cell. We have this cell. We still have a frequency reuse of 1, which means that in our cluster we only have 1 cell. But this cell, we were split it into 3 parts. And let's give it names. So typically we refer to 1 cell as A. Now at this point we'll just refer it as A1, A2, A3. You could think of each of these sectors as an independent tiny cell, right? As an independent tiny cell. And the antenna will be pointing in this direction, and therefore the radiation of the antenna will be here. And so if you proceed to what we did earlier and you do the splitting to all the other cells, you'll notice that your interferers will be here. So now this part here will not see 6 interferers, it will only see 2 interferers. So that's one of the key advantages of using sectoring. Sectoring reduces interference, and that's the key advantage of why we want to sector cells, why we want to have this kind of antenna as opposed to an omnidirectional antenna. It reduces co-channel interference. Now I'll show you another example. So say we have a cluster of 3. Again, take the same picture we've done before without sectoring, and now simply go to the cells and split it into 3, and just go with the same conventions of naming them. So you have your cell A, we split it into 3, so now it's called A1, A2, A3, and so on and so forth. And again, when you have splitting, the channels that you had, and we saw the channels earlier, remember we saw 9 channels, these 9 channels are now split among these different cells. So we have 9 cells, which means that in every sector, 1 channel is allocated. So that's what's happening here. This is a static way for resource allocation. It is not a smart dynamic way for resource allocation, but nonetheless, this is the approach that is used. If you look at, for instance, at this one here, let's look at this sector A1. A1 would see 3 interferers. Only 3 interferers, okay? Whereas before, when we had a complete cell, you used to see 6 interferers. Let's look at a cluster of 4, and if we split a cluster of 4 with 120-degree sectoring, this antenna, this region here, will see 2 interferers. And if we do 7, this antenna that you have here for the region of A1 will see 2 interferers. So again, overall, we've decreased the number of interferers that are observed, the number of cells that could interfere with us. We've decreased them from 6 to either 2 or in this case 3. So this is an improvement, and this is why cellular sectoring is a good thing. And this is why it is used even today. Right? You see these cellular sectoring everywhere. Now, if we move along, and now instead of considering only 3 antennas that are so basically 3 antennas in each being sectored with a 120-degree coverage, let's consider 6 antennas. And these antennas are directional antennas, and they have a coverage of 60-degree. So you could have such a setup. So you have a base station, or you have an E node B that looks like this. So each of them is a separate antenna, and in each of these antennas, it operates with a specific frequency. Okay, and it has a dedicated channels allocated to each of these sectors. So this, again, you'll see it everywhere around cities. Major cities, you'll have this kind of setup. Especially in dense regions. So if we draw the cells that we had before, but now instead of keeping it as one cell or splitting it into 3, we split it into 6, and we give them names. So we call them A1, A2, A3, A4, A5, and A6, and we look at its coverage region. So it's, for instance, if we look at the antenna for A1, it would only have this coverage area, and in this coverage area, it will only see 1 interferer. And again, this is the key advantage of using sectoring. Sectoring reduces the impact of co-channel interference. Sectoring reduces the impact of CCI, co-channel interference. And the more sectoring you have, the more you will reduce the impact of interference. Now we have 6 antennas at your E node B, and the interference decrease. We saw earlier with 120, we typically see 2 interference. Now with 60-degree, we see roughly, in general, you'll see 1 interference. Sometimes you'll see 2, but in general, it's 1. If we look at, for instance, a cluster of 3, you'll see 2 interferers. If you look at a cluster of 4, you'll see 1 interferer. And if you see a cluster of 7, you'll see 1 interferer. So this is a major improvement. So 60-degree sectoring is even better than 120-degree sectoring, and 120-degree sectoring is better than omnidirectional antenna. So far we saw the benefits of having sectoring, and we realized that sectoring actually decreases the co-channel interference. At this point, what we're interested to do is kind of give a summary of the 3 cases, omnidirectional, 120-degree sectoring, and 60-degree sectoring, and then attempt at quantifying the SIR for downlink. So we'll see how to do that. So if we take all that we've showed you in the past slides, this is what we have, right? So if you see here in this table, you have the number of clusters, and we said for practical systems, the number of clusters that make sense are 1, 3, 4, and 7. All the anything above that is, at this point, for these systems that we have until the 2020, these are the practical cluster sizes. And in terms of the different interferers interfering E node Bs that every specific reference E node B sees will be 6 if we use an omnidirectional antenna, a non-sectored antenna, and again it's 6 because we deal with a hexagon, and a hexagon has 6 sides, and we saw them earlier. And if we are talking about an antenna with a 120-degree sectoring, so you can see, you radiate, every antenna on the E node B radiates within a range of 120 degrees angle. Then in that case, in general, you'll see 2 interfering E node Bs, and in this case, when you have a cluster of size 3, you'll have 3 E node Bs, and we showed this as well in previous slides. And we also showed finally that if you have an antenna, 6 antennas on your base station, and every antenna will radiate within a beam width of 60 degrees, then in that case, most of the time you'll have only 1 interferer, except with cluster size 3, you'll see 2 interferers. So again, this, if you were interested to see it, just go back to slide 6, slide 7, and slide 8. You'll have the details there. I just wanted to put it all together in a nice table so we'll be able to compare it. So as you can see right away, that we could observe the following, essentially, that the CCI, the co-channel interference, is decreasing as we increase the number of antennas on the base station. So when we use sectoring, then the co-channel interference decreases, and that's really what we generally want to have. We want to have less interference, and therefore having a sectoring on your antenna is a good thing. Now, I should mention, perhaps I didn't mention it, I naught, this is what we will use right now. I naught is the number of first tier co-channel interference. So I gave you the numbers, but I didn't really introduce this variable I naught. So it is this, it is the number of first tier co-channel interference. We used it, we identified these numbers, but we didn't really have a variable associated with it. So we will use this variable. It will be practical when we do analysis. So this is it. This table is quite useful when you do your mobile network design. You could always come back to this table to do your analysis. Okay. So now at this point, what we're interested to do is to measure the downlink SIR and the worst case scenario. So first of all, SIR, if you do not recall what this is, please go back to the previous lectures. So we had a lecture on SNR, SINR, and SIR. In fact, here we could have seen it. We could have measured SINR, but we relaxed the impact of noise, Gaussian noise, Johnson noise, and we only wanted to see it from a signal. Wanted signal over interference, and that's why we will only look at it from an SIR perspective. But perhaps somebody else would want to include N as well, to noise, and that's fine. There's nothing wrong with that. One is also capable to actually evaluate the SINR. Now, with a couple of things to note is that we are interested to measure the SIR in the downlink. Now, downlink, what this means is that you have an E node B, an antenna, a cell tower, sending a signal, and you are detecting the signal on your UE, on your mobile device or any other device, on your user equipment device. This is because we said this downlink. If we would have said the uplink SIR, it means we are interested to measure the signal quality at the cell tower. Whereas right now, when we say we want to measure the downlink SIR, we want to measure the signal quality on the mobile unit. We want to measure what is the quality that the mobile sees, this device here. And we said we want it to be at the worst case scenario. So worst case scenario, what it means is that we want it to be the farthest away from your cell, right? The farthest away from your cell while still being in the cell. So what this means is basically to be at the edge of the cell. So anywhere on the edge of the cell should be fine. We'll just put it at the corner. This is the longest range, right? So from the center of the hexagon to this should be a length of size L, if we assume that every side is of size L. Okay, so this is the longest range on the cell. You could have also put it here, 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 or here. That's fine. So all of these points will give the worst case scenario at the cell edge. Now, the way we do the analysis is as follows. So before we do the analysis, I want to show you the equation for the channel. This is how we will proceed. So essentially, this equation kind of resembles the Freq equation with some modification so that it is specifically tailored for mobile communications. In here, what you have is you want to find the power at the receiver. So the receiver for us is this device, the power at the receiver, measured d from a distance of d away from the base station, away from the E node B. This is the distance from the E node B, d. D is just some generic variable for that. And it is equal to the power received at some distance d naught. This d naught is referred to as a close-in distance, and in general, this you can measure it. During exams or evaluations, I will give you this value. So you do not need to figure this out. But in general, if it's not given to you, you could always assume a free space path loss to find the power received at the close-in distance. So you could always do that. But in general, in evaluations, I will give you this value. And then what you have is you have the distance. How far are you away from the transmitter? In this case, the transmitter is this one, the cell tower. How far are you away from the cell tower? We said that is the worst case scenario. Therefore, you will be L meters away from the cell tower. So you could just write that here. And then d naught is the close-in distance. You just have it in the bottom, and you have to the power of minus n. Remember, in free space path loss, the exponent that we worked with was exponent of 2, right? So minus 2 if you bring it up. So exponent of 2. So when we talk of free space path loss, so in general, free space path loss makes sense when you are in line of sight, or when we talk of satellite communication. The path loss exponent for free space path loss is 2. When we talk of cellular communication, the path loss exponent could vary. And in fact, the feasible number, the feasible values for the path loss could be anywhere between 2.7 to 5 for the path loss exponent. However, I should admit to you that perhaps selecting something between 3 to 5 is better, especially if we are talking of deployment and measurement in an urban city, so in a city, and that this received signal is highly impacted by shadowing, so different objects in the channel. So if that's the case, which is generally a good consideration, if you do your measurements in a city, in a built-up city, you could consider a value for the path loss exponent anywhere between 3 to 5. So we will just consider the kind of middle point between 3 and 5, and then we generally will use n equals to 4. So here you would simply enter minus 4, and that will take care of this part here. Okay, so this is the equation for the channel loss when we work in mobile communication. This is an important equation. It will show up in other places. In fact, we did discuss it in previous lecture, but I wanted to kind of give you a refresher. And so this is the close-in distance. This is the power, received power at the close-in distance. This is the power at any distance d, and this is the path loss exponent. And the path loss exponent for mobile communication should be considered to equal 4. Okay, so now we have this. So what we do is essentially we measure the SIR, the signal to interference ratio, And again, we don't look at it from noise. Now here I realize I made a typo. This N should actually be an I. It should be an SI, S over I, so not N. So this is wrong. It should be an I here. S basically means the good signal that you are getting from your transmitter. So essentially here, you could simply replace it by the power received at a distance L from your transmitter. The transmitter is this one here, and this is the receiver. So the power received at a distance L. And for this, you could simply use this. So whatever you have here, except instead of D, enter L and then plug it in here. So this is just some constant, just rewrite it. And then here you enter L over D naught to the power of minus N. And in the bottom, we are interested to find noise and again to find interference. And in fact, we are interested to find the aggregate interference seen by this device. Now, how do you measure the aggregate interference by this device? You could basically measure all the different interferers. So basically, you could measure this distance from this point to the mobile unit, this distance, and so on and so forth. However, this could be a bit tricky and it could take some time to do the analysis and the math and all that. But what you can do is you can actually use the distance from these points, these co-channel cells, to the center of your cell. So this is not really what you wanted to get. You are interested to measure it at this point, but you already have the distance up to this point. So you could use that, and instead of saying it's going to be 100% accurate or 100% exact, you could just put an approximate, because you'll get a measurement of your interference, your aggregate interference, and it's going to be a reasonable estimate. And therefore, we use this expression here because we're estimating. Now, we say the power that you receive at a distance DFR, we said this radius, the co-channel radius is basically represented by DFR. And why do we include I naught here? Well, we include I naught because we have I naught co-channel neighbors, right? So in here, we, as you can see, we have 1, 2, 3, 4, 5, 6 I naught neighbors, and that's why we write I naught. We just keep it generically because what if we want to do it with sectoring? We could just pull in any value from the table and plug it into the equation. So, but in general, we could just write I naught to keep it generic. Okay, so at this point, what we do is we simply use this equation for both for the wanted signal and the interference signal. And these values that you're doing, they're essentially the average power that you get from your E node B to your mobile, and this is the average power that you get from your from all tier 1 E node Bs, right? So these are all tier 1 E node Bs measured to your mobile unit, to your UE. So we plug in the values, we put in L instead of D in here, and we rewrite it. We put DFR here instead of anything else, and we rewrite it below. And if we do some cleaning up, so some analysis, we remove certain variables. We cancel this and this. We could cancel the D naughts. We could then flip it. So essentially we could have DFR on top, L in the bottom to the power of N, and we have I in the bottom. And if you recall, we saw before that this value here is in fact equal to the square root of 3N FR times L. So instead of this, I could simply rewrite it as such. We saw this in the previous slides, and I highlighted it over there. So we could just plug it in this expression, and then this difference, not a difference, but if we take the top, we divide by the bottom, we could remove the L, so that's gone, and we could simplify a bit, and we will eventually come up with this equation. And this is the interesting equation that we will use specifically when we measure the downlink SIR at the worst case scenario. This is not an exact one, but it is a reasonable approximation. It is an approximation that is accepted and used to right away and quickly understand the approach for designing a mobile network. Okay, let's continue. So in here, I wanted to show you an example of how we could do these measurements. So let's go through this example. The example is we have a UE at the cell edge. So let me get my laser pointer. So a UE at the cell edge is required to have an average SIR of at least 15. So at least 15. So if it's more than that, that's desired, but at least 15. You cannot go below 15. Assuming the serving E node B antenna is omnidirectional, so it radiates in all directions, design the mobile network by suggesting a feasible cluster size. So we want to know what is the cluster size required that will guarantee that we get 15, at least 15 SIR. So let's go and do the analysis. Number one, if we have SIR and we know it's 15, let's change it from dB scale to linear scale. So what we do is we have our 15. It's also equal to 10, 15, the dB divided by 10. And so that becomes 10 to the power of 1.5. And then we use the calculator and we discover that 15 dB is in fact equal to 31.6 in linear format. Now, we want the SIR to be at least 15, which means that the value of the SIR should be equal to this or should be bigger, because we're saying it's at least, so it should be bigger. And therefore, we're going to use this arrow as such, bigger or equal. And then now, for the rest, we just use the equation that we showed on the previous slide, and we rewrite it here, which is 3 times the cluster size divided by I naught to the power of n over 2. Now, we said this is a mobile communication. So when you read it, this is for mobile communication. And in mobile communication, assuming a mobile communication with shadowing, a path loss exponent of 4 in an urban environment makes sense. So we'll simply enter 4 for the path loss exponent. For the I naught, we know that for an omnidirectional antenna, if your E node B is omnidirectional, you will have 6 interferers, and this comes straight from the table that we had on the previous slide. So we could simply write 6 here. And if we simplify some stuff, we could rewrite 3n FR. 4 divided by 2 is simply 2, 6 in the bottom. I realize I forgot an equal sign here, so that's another mistake. So it should be an equal sign here. 9n FR squared divided by 6. 9 divided by 6 is equal to 1.5 n FR squared. Okay, so now we have this and we have this. So basically what we're saying is 31.6 is it is less or equal to 1.5 n FR. And if we do some analysis, or we can simply rewrite that 1.5 n FR is greater or equal to 31.6, we could divide by 1.5. So we bring it on this side, we get 21.07, and then we take the square root, and then we'll figure out that the NFR, the cluster size, should be greater or equal to 4.59. However, we saw that the sizes of the cluster or the valid sizes of the clusters are 1, 3, 4, and 7, right? There are others as well beyond 7, but these are the ones that we want. These are the ones that are practical. So if we want an NFR greater than 4.59, this basically means that we have no choice but to use 7. This is the next one that is valid that can be used. Okay? We could do some sanity check, and we could do some verification to see if what we got makes sense. So perhaps you might be uncertain. Should you write in your design, should you suggest a cluster size of 4 or a cluster size of 7? You could always try it. You could always try it and see what the result what the result you would get with both of them. So if you use an NFR of 4 and you do some analysis, you'll figure out that your SIR is 13.8. And this is not good, because we said we want an SIR that is at least 15 dB. And here you get 13.8. So that's not good. If you use an NFR, so a cluster size of 7, and you put it in the equation, you'll find an SIR of 18.7. And this is good. This is certainly bigger than this, and so receiving this should be fine by your on your device, right? So this is what you want. So in other words, this is a correct answer. There is nothing wrong with it. We just did this just as a way to reassure you of why we picked 7 as opposed to 4. There's also a table that I'd like to show you. So in this table, it kind of shows you the typical values of the SIR in mobile communications. So if you have an SIR of greater or equal to 20, you have an excellent signal. If you have an SIR between 13 and 20, that's good. Anywhere between 0 and 13, that's fair or poor. And less than 0, or is equal or less than 0, then there is no signal. So this is kind of a good chart to know in terms of the quality. So having an SIR of 15 should give you a good signal at the edge. So that's not bad. You are at the edge and you are getting such a signal. This is not a bad outcome. Now, one last comment before we wrap up the lecture is that we said that the size of the cluster has 2 impacts. So on one hand, we want the size of the cluster to be small, because if we have a smaller size of a cluster, we'll be able to accommodate more channel bandwidth to users. We'll be able to have more simultaneous users within a single cell. However, we also noticed through this equation, right, the equation for the SIR, that the bigger the cluster size, the larger the SIR, and we want a large SIR. So now we are in an internal battle. On one hand, we want a smaller NFR, but on the other hand, we want a larger NFR. We want a smaller NFR because it allows us to have more channel for and therefore more users. But we want a larger NFR because it improves the quality of the signal. It brings us in the excellent slice here. So what do? This is where engineering expertise and design is required. This is where trade-offs come into play. There is no solution that will be perfect in all circumstances. So this is where you have to decide on what makes sense at what point, right? But you cannot have you cannot have the best of both worlds. You cannot have good quality of a signal and also many users at the same time. But rather you could find a compromise between how many users can you accommodate while having a reasonably okay signal. So this is where a trade-off comes into play, and this is where the expertise of an engineer, a network designer, an engineer is shown. So that finishes this lecture at this point. Now in here, I wanted to show you some of the references that I used in here. So you have them here. There's also the link for these references. They essentially discuss the fundamentals of mobile communication. I will also put it below the video. So you'll have the link below the video in case you're interested to see some of these sources related to this lecture. And that's it. So that's it for now. Thank you for your attention, and And for your exam, that essentially covers it. The material that we have. But your exam, just I'll write some note to you on Slate. But essentially, your exam will be open book, so you'll have access to all the notes that you have, all the slides. So you'll be able to do that. And then I also will provide you a formula sheet, but essentially you have all the slides that at your disposal. You could just look at whatever notes you want. It is open book. Thank you for your attention, and good luck with your final exam.